Okay, so we've seen that you can program over lists using a program with lists using recursion as a fundamental way of manipulating lists of arbitrary length. I'm going to look at, very briefly, a number of other ways of dealing with lists, principally something called list comprehensions. So list comprehensions is a style of programming with lists that was popularized by Haskell and isn't today found in a number of other programming languages. Some of you may have seen something very similar in Python, for example. That was directly inspired by list comprehensions in Haskell. So before we get into that, I can show one cute thing we can do with lists and any type which can be enumerated, listed in order. For example, numbers. We can look at things like the range of numbers from 1 to 10, and that can be written with this dot dot notation. And you can even do things like with intervals 1, 3 up to 100, and then you sort of do jumps of 3, making sure you never get bigger than the value 100. And you can count down in the same way. You can go from 100 to 99 and down to 0, for example. Too many commas there. 99 down to 0. You can do it with other kinds of enumeration types. For example, you can enumerate characters. So you can go from A to Z. Kind of useful thing to be able to do. And that gives the list of all the characters between from A to Z. And remember that a list of characters is the same as a string. And when Haskell prints a string, it prints it in this nice string notation. Okay, that's a very simple way of building lists. We're going to look at a bunch of ways of processing lists using something called a list comprehension. So let's suppose we have a list of things. Let's give an example. Let's use this example actually, 10 things. So we've got this list of 10 items, 10 numbers, calling it 10. Now let's suppose we want to compute the list of, which is like this list but with every number doubled. So we can build that using a list comprehension. We're going to build a list of 2 multiplied by n for every n taken from the list 10. So this is a list, happens to be the list from 1 to 10, but it could be any list you like. For every number in the list, we're going to take every number in the list. This is called a generator. It's going to generate every number in the list, and for each number it's going to multiply it by 2. So this will be like the list we started with, except with everything doubled. So this can be any expression you like that uses n or not, if you don't want to use n. So here's a little example or a little puzzle that you can think about for a second. I'm going to pause the video. What do you think this thing will give you? It will give you 10 copies of the number 1. So for each number in the list, it will produce a 1. Whereas this example, for each number in the list, it will produce 2 times that number. Okay, that's the basic elements now. So let's look at another example. Let's look at all the odd elements of a list. So let's compute all the odd elements from this list using a list comprehension. So we're going to produce a list of numbers n. Those numbers are going to be taken from the 10 list in this example. But we're only going to keep the numbers if they're odd numbers. And there's a little function called odd that will tell us whether a number is odd or not. So odd 1 will return true and odd 2 will return false. And this part of the list comprehension is called a guard. It decides when we keep elements n. So we keep all the n's for which this expression is true. It'll keep all the odd ones, namely 1, 3, 5, 7 and 9. And we could combine those two ideas. We're doubling every odd element by doing 2 times n. And so then we see all 3 features of a list comprehension that we've seen so far, all in one example. We have an expression that we're generating from a generator and a guard. So these things are pretty powerful ways of programming with lists, often as an alternative to using recursion or other functions. Let's take an example with multiple generators. So we can build examples where we have not only numbers taken from, in this example, we're going to take a character as well as a number, and the characters are going to be from the characters, well, let's take it from the string ABC, 3 characters in that string. And what are we going to build from that? Well, let's see what we can do. Let's take a smaller list here because I think this is too big too quickly. Let's take this from the list 1, 2, 3, and let's build a list of pairs. We haven't seen pairs for a little while, of a number and a character. So maybe you can guess what this will produce. It will produce, for every combination of numbers and characters, pairs of the number and the character. So it's not going to pair 1 with A, 2 with B, and 3 with C. It's going to take all combinations. It's going to take for every element from this list, it's going to take every element from this list. So you get 1A, 1B, and 1C, then you get 2A, 2B, and 2C, and so on. If you want to pair them up one by one, then we need to use a different function for that. We'd actually use a function called zip. We wouldn't use a list comprehension at all. And of course, just as with the other examples, we can combine this, if we want, with a guard. So we could only take, for example, we could take just the even numbered n's and generate only this when n is even. Well, there's only one even number in this list. It's the number 2. Whereas if we took the odd numbers, we'd get a slightly bigger example. Okay, so that's an example of generating lists with multiple generators. So I've done all these in the interpreter, but we can use these freely in our function definitions. And so I'm going to end up by looking at an example that I introduced in the very first part of the lecture. If you're watching the live lecture, I gave an example of how you can sort and how you can write a function which is in the spirit of an imperative algorithm called quicksort, which was invented in the 1960s, which is one of the efficient ways, relatively efficient, simple ways of sorting a list. So we can implement a quicksort-like algorithm. It's not really exactly quicksort because it's using dynamic memory allocation behind the scenes, whereas quicksort is an imperative in-place sorting method. But the idea with quicksort is to sort a list by the following intuitive procedure. If you're sorting a list of elements, then you take the first element of the list and you arrange all of the smaller elements on the left side of that list, and all the bigger elements of that than that element, or bigger than or equal to elements on the right side, and you recursively sort those two sublists. So we can write that using a combination of recursion and list comprehensions. I'll call it qsort, and we're going to define it in the most common recursive form, which is to have a base case of being the empty list and a non-base case being a list with at least one element. And sorting the empty list is, of course, very easy. Sorting the empty list gives you back the empty list. The idea for sorting a non-empty list, as I said, was to take all the elements which are smaller than the first element and put them on the left. I'm going to call that the smaller elements. We're going to put those on the left. And we're going to put this element in the middle. So how do we do that? Well, we're going to use this operation for joining lists together. But it joins lists together, and this is not a list, this is a number. So we're going to make it into a tiny little list, like that. And we're going to take all the bigger elements and put them on the other side. And I haven't actually said what these are yet. I'm just sort of intuitively saying, well, if we put the smaller elements on the left, the bigger elements on the right, but what we're going to do is recursively sort them. So we're going to sort all the smaller elements that we put on the right, and we're going to sort all the bigger elements and put those on the left. Now the key to make this work is, of course, that there'll be fewer elements to work on here than we started with. and there'll be fewer elements here than we started with. So eventually, when we keep recursing, we'll eventually always get down to the base case, which is an easy case to sort. But to finish this definition, we can add a local definition to define the smaller elements. Now, a local definition can use any of the parameters that we have, and that's a good thing because we're going to use them both. We can use a list comprehension, something of that shape, to define all of the elements. I'm going to call them the S's, the smaller elements. Where do the S's come from? The S's come from the rest of the list. And which ones do we want? Which S's do we want? We want all the S's which are smaller than or equal to the first element n. And similarly, we can look at the bigger elements. Well, they're all the bigger elements, I'll call them a B, where B's are also taken from the list of the rest of the list, but where the elements B are bigger than the element that we put in the middle. So they're all the bigger elements, they're all the smaller elements. We put the smaller ones on the left and sort them, we put the bigger ones on the right and sort them, and we jam n in the middle, and there we get our sorted list. And we can Q-sort. Let's sort something like, let's take the numbers from 100 to 200, join together with the numbers from 1 to 10. So it should be able to put all those 1 to 10 guys on the left-hand side, otherwise it's a bit of a mess. And indeed there they are, they're the numbers from 1 to 10, and that's the rest of the list from 100 to 200 in the blink of an eye. So that was a very quick introduction to list comprehensions and an example that actually nicely combines recursion and list comprehensions. Very often you'll be faced with a choice of using recursion or list comprehensions, but this example usefully uses both of them in a single example.